At this point, we've seen two important things about equilibrium at a given temperature. The first is that at equilibrium, delta G equals 0. There's no available energy to do work. All of the work has been done. Also at equilibrium, the ratio of products to reactants is a constant, K. This is because the rate of the forward reaction is the same as the rate of the backwards reaction. You'll remember from our kinetics lessons last term, the rate is equal to a constant K times the concentration of the reactant. That means that the reverse rate is equal to a different constant times the concentration of the product. And since these two rates are equal, then the ratio of the forward constant to the reverse constant is the same as the ratio of the concentration of the products to the reactants at equilibrium, and this is the definition of our equilibrium constant, K. Now, we've said all along that thermodynamics deals with energy and kinetics deals with time. If we have a way to connect tabulated standard thermodynamic data to the ratio of products and reactants at equilibrium, then we would have a tool to bridge the gap between spontaneity and speed. To start with, we're going to use our thermodynamic relationships to turn Gibbs' equation into variables a bit less abstract than enthalpy and entropy. For every infinitesimally small change in enthalpy, temperature, or entropy, we get a change in Gibbs energy according to this equation. So let's go through and make some substitutions according to relationships that we already know. For a closed system doing no non-expansion work, we can also replace the change in internal energy with the temperature times the change in entropy minus the pressure times the change in volume. And if we simplify the terms, we end up with the change in Gibbs energy is equal to the volume times the change in pressure minus the entropy times the change in temperature, which is also called the fundamental equation of chemical thermodynamics. Now, this equation gives us two pretty cool insights. First, at a constant pressure, entropy is equal to the negative change in Gibbs energy per change in temperature. Now, because entropy is positive for all substances, this tells us that Gibbs energy decreases as temperature increases, and that the rate of change with temperature is greatest when entropy is greatest. Second, at a constant temperature, volume is equal to the change in Gibbs energy per change in pressure. And because volume is always positive, delta G always increases when pressure increases, and that the rate of change is greatest when the volume is the greatest. Taken together, we should see that for a pure substance, the effect is going to be stronger for the gas phase than it will for a liquid or for a solid, since a gas phase is when both the entropy and the volume per mole are at their highest. We can also think of dilute solutions as similar to gases in this way, since they also have a high molar entropy and a molar volume. The major difference is that we use partial pressures for mixtures of gases and concentrations, or moles per volume, for substances dissolved in solution. Let's use gases to get back to our search for a connection between Gibbs energy and the equilibrium constant. Firstly, because we've shown that the relationship will be strong for gases. Second, because we know that at least in some cases we can simplify by using the ideal gas law. And third, because we already know the pressure for the standard Gibbs energy at 1 atmosphere. So to find the difference between the Gibbs energy for 1 mole of a gas at standard pressure and at any other pressure, we can restrict it to a constant temperature to get the change in Gibbs energy per mole equals the volume for 1 mole times the change in pressure. So in order to find the Gibbs energy per mole at the final pressure, we just need to start at the Gibbs energy per mole at standard pressure, and then add the integral from the starting pressure, or the standard pressure in this case, to the final pressure of the molar volume integrated according to pressure. Now here's where we can assume ideal gas behavior, because the molar volume, or volume per mole, is equal to RT over the pressure. And that means that the integral is just RT times the ln of the final pressure over the standard pressure. This already is pretty useful because we can now use it to identify the Gibbs energy for a system at any pressure, as long as it can be modeled as an ideal gas. But let's take it a step further to find the delta G of the reaction for a generic reaction, like A moles of substance A plus B moles of substance B get converted into C moles of C and D moles of D. We know that we can calculate the delta G of the reaction as the Gibbs energy of the products minus the Gibbs energy of the reactants. Which, with a little simplification, we can get which we can read as the Gibbs energy of the products minus the Gibbs energy of the reactants under standard conditions. That gives us the standard delta G plus the gas constant times the temperature multiplied by the natural logarithm of the pressure of C raised to the stoichiometric value of C times the pressure of D raised to its stoichiometric value divided by PA to the A times PB to the B. And this construction, whether we want to do it in partial pressures or in concentrations, is exactly what we've already used to say this is the concentration of products over the reactants. But in this case, we're not yet at equilibrium. We've made it completely general, so these are arbitrary amounts of the products and the reactants at any point in the reaction. So this is what we're going to call the reaction quotient, Q. And we can rewrite that whole mess as delta G of the reaction equals the standard Gibbs energy of the reaction plus RT ln of Q, where Q is the concentration of the products over the concentration of the reactants, raised as necessary to their stoichiometric values, and this can be either partial pressures or concentration of dilute solutions. Now we said we wanted to use something about equilibrium. So that means we need to make one more constraint, that the delta G of the reaction is equal to 0. Well, that means that our standard delta G of the reaction is equal to the negative RT ln Q. Now we've constrained the concentration of the products and reactants to what they are at equilibrium, because we've set the Gibbs energy of the reaction to the equilibrium value of 0. So this is now where we can fill in our value K. And this becomes an extremely useful result, because now we can go back and forth between the standard thermodynamic data of enthalpy and entropy and Gibbs energy to determine the ratio between the products and the reactants of an equation at equilibrium. And we've also, while we were at it, found a way to generalize that to what the Gibbs energy of a reaction is at any stage in the reaction. Another way of writing this is K equals e to the negative delta G reaction over RT. Now the form of this reaction might strike you as similar to the Arrhenius equation, which I can remind you is K equals A, some constant A, times e to the negative activation energy per RT. So now we, in both cases, have an exponent raised to the negative of an energy divided by the gas constant at a temperature. And Gibbs energy now is playing the role of activation energy, which means that we should be able to find the enthalpy and the entropy of the activation of the reaction too. Following this line of thought leads us down the path to transition state theory that unfortunately lies beyond the scope of this course. However, we can use this idea of energy and equilibrium to begin to understand why reactions that seem similar on the surface can still have a big difference in strength, or what we might call chemical potential. We'll start down that line of thinking with what might be the simplest reaction of all, the losing or gaining of a hydrogen atom.